Okay, I think we can continue. Okay, can you hear me?
Yes, doctor.
Yes, doctor.
Yes, doctor, can hear you.
Okay. Now we do one example related to the topic that we have learned. So this example you can find it in the textbook, which is the PC Sen, page 9. But there is some difference in the value. We the one that you will book with this one. Okay? The one in the book and this one, there will be some different in terms of value. But I think all the rest is the same. Question is the same. The magnetic construction is the same. So dimension of the relay system are shown in figure below. The magnetic core is made of cast steel whose BH characteristic is shown in figure 1.7 in page 6 of the book. The coil has 300 turns and the coil resistance is 6 ohm. For a fixed air gap length equal to 5 mm, this source is connected to the coil. So basically, we have a coil, light, okay. A DC source is connected to the coil, so we connect a DC source to generate flux in the core. To produce the flux density of 1.1 Tesla in the air gap. So B here is 1.1 Tesla. Calculate the voltage of the DC source. So we have to find what is the voltage here. So basically, if you want to find the voltage, you have to find the current. And it is mentioned here the coil is 300 and the coil resistance is 6 ohm. So it's already given the number of turns. So you have to find what is the current first. Okay, and then when you find the current, this is electrical circuit. For electrical circuit, basically, this can be modeled as let's say it is an inductor. Ideally, in DC, what happened to inductor? When we operate with DC voltage, what happened to the inductor in DC? Short circuit. Very good. It will be short circuit. But we define it as non-ideal inductor. So what happened is the coil resistance is 6 ohm. So basically, here, this is the VDC. Okay, this is not magnetic circuit. This is the electrical circuit itself. Okay, so the inductor will not shorted, but it has 6 ohm resistor inside it. So in order for you to find voltage, you have to find current. Okay, and the number of turn is given here, 300. So you already know N. You have to find I. So basically, you know what method to use. Okay. Basically, you can see what method that you can use to solve this. As I said just now, N is given, I you have to find, okay? So what is the value of I? So you have to find, and from here we know that we can use the Ampere circuit law, which is HC LC plus HG LG. So if you want to find the current, you just divide this with N. Okay, so then you get the current. So now you have to find HCLC and HGLG. So how to find HCLC and HGLG? So we know that H is magnetic field intensity, which is based on a magnetic field density, and it is given here the BH characteristic of figure 1.7, which is here, which is this one. Okay, so this is figure 1.7. So this is figure 1.7. Okay, let's say I zoom in.
Doctor?
Yeah.
I think, okay. It's moving now.
Okay, it's moving.
Yeah.
So what is the value of the flux density that we want? 1.1 Tesla, is it? It is mentioned here in the question. 1.1 Tesla. So we want at the air gap, the magnetic flux density is 1.1 Tesla. So we look here, 1.1 Tesla. Where is 1.1 Tesla? Here. And the material is what? Cast steel. Material is cast steel. Cast steel is this magnetization curve. This one in the middle. This is cast steel. So 1.1 here. Okay. So based on this cast steel curve, we can find the hash by extrapolating the graph. Okay. So 1.1 Tesla will give you around 800 ampere turn per meter. Okay. So what you get is HC for the core is equal to what? 800 ampere turn per meter. Okay. So now we have to find LC, HG, and LG. Okay. So what is LC? The length of the core. So can somebody help me? What is the length of the core? It will be from here to here, plus here to here. So basically, we can divide it into two parts here. This one, right? And also this one. Okay. Sorry, okay. 10 plus 5. Wait.
I think it's 32.5 centimeter, I think.
32.5?
Yeah, 10 plus 2.5.
So this is 5 cm, 10 plus...
Is it 5 cm or 2.5? The width?
The width is 5. The width is 5.
Sorry.
This one is 5. So 10 plus 5, 15. From here to here is 15, is it? Right? From here to here, 10 plus 2.5 plus 2.5, we get?
15.
We get what?
15.
15 centimeter plus this one is also 15 centimeter. On the top here is what?
15.
Again, it is 15.
10 centimeter.
So 15 centimeter. At the bottom here also 15 centimeter. Okay, so these are the length of the core. So we have to convert to meter. So it means that what? 0.15 multiplied with 4, is it? So what is it? Anybody help me? 0.6. Okay.
0.6 meter.
So we get 0.6 meter for LC. Okay, so we are done with LC. Yes?
Doctor, I have a question, please.
Yes.
Why we didn't take the whole length? Why we only took the one with the red part?
The one? What?
Why we didn't take the whole length of the iron core?
This one is not the length of the whole iron core. Do you think this one is the length of the whole iron core or not?
No.
Why?
Because we took the height as 15, not 20.
20.
With 15, we took 15, or not 20, right? LC is supposed to be the length of the core, right?
Yeah. The red line here.
Why the red line here?
The length of the core. From here to here, to here, to here, and also for the eye is here. So basically, if I draw something like this, without the air gap, let's say I put it, because either you have air gap or you don't have air gap, it's the same. So this is the line, the green one. Okay, so this one is 10. This one is 2.5. This one is 2.5. So this one you get 15. This one is 10. This one is what? This one is 10. This is again 2.5. This is again 2.5. So at this side you get 15, 15, 15, and 15.
Okay, Dr. Alex.
Okay. So we get 0.6 meter. Next is Hg. So Hg is equal to B divided by mu naught. As I said just now, B equal to mu H, and we know that B equal to mu, B equal to mu H. If you want to find the gap, this is at air gap. Okay. So for sure this is for air gap. This is for sure for air gap. This is 1.1 equal to the mu for air gap is equal to mu r multiplied with mu naught. For air, mu r is 1. So what left is just mu naught multiplied with Hg. So Hg is basically 1.1 divided by mu naught, which is what? 4 pi times 10 to the power of minus 7. That is Hg, the field intensity of the air gap. And the air gap itself is, what is the length of the air gap? 4.4 millimeter. So what is it? We have 2 air gap. So it should be 2 times 0.004, is it? Millimeter. So we get 0.008. Okay? Any question until now? So what is basically Hg here? Can anyone calculate this for me?
Hg is 857,352. 875,352.
75 352
352.
352. So this is H equal to, I think this one is more than enough. No need to have the point. Ampere turn per meter. If we can find the current, just plug in all the value. Hc is what? 800 multiplied with Lc. Lc is what? 0.6 plus Hg is 875,352 multiplied with Lg is 0.008 divided by number of turn is how many turn? 300. So what is the current?
Doctor.
Sorry,
24.9.
24.9 ampere. So this is the current that you should supply at the coil so that you can get 1.1 Tesla at the air gap. Okay, and we are not done yet because the question asks for voltage. What is the voltage that you should supply? So the voltage is equal to IR. The current is 24.9 multiplied with the resistor. What is the resistor? 6 ohm. Okay, so what is the voltage?
149.6.
149.6. It practically is around 150 volt. Okay, so this is the voltage that you should supply. So we are done with the first question. Okay, so now we go to the second question, which is the stored field energy. Stored field energy. So if you look at the second question, the field stored energy is actually WF. Okay, it is actually WF, capital WF. And we have learned that it is equal to WF at the core plus WF at the air gap. It is the field energy stored at the core and also the field energy stored at the air gap. So what is the WFC here? It is the field density of the core multiplied with the volume of the core, right? And this one is the field density of the air gap multiplied with the air gap volume. Okay, so this is the basic equation for the field energy. And we know that this one is equal to the integration of H dB. If you look again here, it is the H integration of H dB. Okay, so based on the plot, if you have B and then you have H and you have the magnetization curve, basically this integration is what? This area. It is this area. Okay, so if you look back at the question and we go back to our BH curve here, okay, if you look back at our curve here, so how can we find that energy density at the core based on this BH curve? It is actually this area, correct? It should be this area. So how to get this? One of the simplest way is to get the approximation of this area. So WFC, the small WFC, which is the energy density, is actually the length of the magnetic field density B, which is 1.1. The length here is 1.1, multiply with the hash, which is 800, divided by 2. So as you can see, it is almost half. Because if we consider this curve, this magnetization curve as a linear, it is almost linear, but it is not linear. So we can say that it is almost equal to the area divided by 2. It means that B multiplied with hash divided by 2. Okay? So this one we get what? Around 880 divided by 2, you get 440. Okay, 440. This is energy field density. As I said just now, the unit is joule per meter cube. Okay, so we are done with the energy density of the field or the energy density of the core. Okay, the field energy density of the core, WFC, is 440 joule per meter cube. Next is what? We have to find the VC. What is VC? VC is the volume of the core. Okay, it is the volume of the core. So basically, how to get it?
Length and width and height.
How to get the volume of the steel?
Length and width and height. Doctor, can you hear me?
Sorry. I want to drink first.
Okay.
Sorry. So, sorry. Again, what is the volume of the core?
The area multiplied by the height.
The area. The volume is the area divided by the depth, is it? Because this is a three-dimensional. Okay, so we have to find the volume. We have to find the volume of this construction here. So basically, one of the method is, okay, you find what is this one, what is this one. This is 15 multiply with 5, multiply with 10, so you get this area, multiply with 10, so you get the volume of the upper part. The lower part is the same, so that one is multiply with 2. Okay, so we write down first 15. This is 15. The length is 15 because 10 plus 5. Okay, so this is VC is equal to 15 is what? 0.15, is it? 15 centimeter, 0.15 meter. Multiply with this one is 5. Multiply with 0.05. Multiply with the depth. What is the depth? 0.1. 0.1. And we have the upper and the lower section. Multiply with 2. So we are done with that. Plus, now we look at this part. It is 10 multiplied with 5. Okay. This one is 10, which is 0.1, multiply with 0.05, multiply with the depth, the thickness, which is 0.1. Okay, so we are done with this. We are done with the upper section, left section, lower section. Now we look at this one. What is the volume? 5 multiply with 10 plus 5 plus 5 is equal to 20. 20 multiply with 10. 20 is 0.2. 20 centimeter is 0.2 meter. Multiply with the 0.05. And then multiply with the depth, which is 0.1. Okay, help me calculate this. 0.15 multiply with 0.05 multiply with 0.1. This is for the upper section and lower section, so that's why you multiply with 2. This is the left section of the core. This is the right section, which is the single eye core. Anyone can help me? Sorry. Hello?
0.003.
0.003 meter cube. Is it? Okay. So this will be 3 times 10 to the power of minus 3 meter cube. So we are done with that, with the with the core. Now we go to the air gap. So how we want to find the energy density of the air gap? If you look back at the equation, it is actually what? B squared divided by 2 mu naught. So we can simply find WFD, the energy density of the air gap, equal to B squared divided by 2 mu naught. So what is B? 1.1 squared divided by 2 times, what is it? 4 pi times 10 to the power of minus 7. What is this?
481.
481. Only 481.
443.
481 or 441?
481. 443.
Is it 481,000?
Yes. 443.
Okay. So the unit is again joule per meter cube. Okay, so we are done with this. The last one is the volume of the air gap. So what is the volume of the air gap? Sorry. What is the volume of the air gap? So for this air gap, the volume is what? 5, which is 0.05. Multiply with the air gap. What is the air gap? 4 millimeter, is it?
0.004.
0.004.
0.4 millimeter, right? 0.004. And then the depth is 10, 0.1. And we have 2 air gap. So this will be the volume of the air gap. So what is it?
It is 4 to the multiply 10 to the power of -5.
4
multiply 10 to the power of -5.
-5, it is a volume, so meter cube. So now we have to write down all this value to here. Okay. So basically, we can find this first. Which is WFC, which is WFC is the energy stored in the core. It is the energy field density of the core, which is what just now? 440. Multiply with the volume here, 0.003. And then the energy at the air gap, which is 481,443, multiply with the volume of the air gap, 4 times 10 to the power of -5. And finally, we just add up these two. So what is 440 times 0.003?
1.32.
1.32, and this one?
Yes, and this one 19.25.
19.25, very good. So this is joule, this is joule. So when we add up together these two, 1.32 plus 19.25, we get what?
20.5.
20.57 around. Okay, joule. So this is the total energy stored in the magnetic construction here. This type of magnetic construction, as you can see here. So the stored field energy is 20.57 joule. And as you can see here, most of the energy, where is the most of the energy stored? Air gap. In the air gap. So even though the air gap is very, very small compared to the core, so most of the energy is stored in the air gap. 19.25 joule. Only almost smaller than 10% of the energy stored in the air gap is stored in the core, which is 1.32 joule, less than 10%. So more than 90% of the energy basically is in the air gap, as you can see here. Okay. So this is one example that show the field energy that's stored in this type of magnetic construction or magnetic system. Any question?
No question for now.
No question for now. Okay, good.
Doctor, can you save that example in PDF?
Okay, I'll give you later on.
Yes. Okay.
If not, you can just watch this video. I'm recording this video.
Oh, okay, sure. Thank you.
Okay, I'm recording this video.
Excuse me, doctor. So for the record, we will give us in the e-learning or in the WhatsApp group?
E-learning.
Okay, doctor.
Okay, I hope it's okay. I have not recorded for many months. I think about 3 to 4 months. I hope it's still okay. Sometimes the software is not working. So even though I turn on the recording, sometimes it's not recording. I hope it's recording. Okay, any question regarding this topic? So in this magnetic system, we have learned that even though the air gap is very small compared to the core, so most of the field energy that we learn here, most of the energy is stored in the air gap. So air gap plays a very important role in storing the energy in the magnetic system. Okay. So can we continue? Maybe a few topics more. I'll explain about energy and co-energy. What does it mean by energy and co-energy? That's all. Okay. Energy and co-energy. So the lambda I characteristic of an electromagnetic system depend on the air gap length and BH characteristic of the magnetic material. As I said many times, so this is lambda, this is I, whereby it is proportional to B and hash. So basically it is a B hash curve. Okay. So let's say you design a circuit without an air gap. So this will be the magnetization curve, or this is the curve of the B hash. Okay. This is the B hash curve. But when you increase the gap, what happens is you can, in practical, you can operate with higher current. Let's say you want the system to operate at 1.1 Tesla. The current without air gap is around 1 ampere. But if you introduce air gap, you can have higher current. You can operate at higher current, maybe around 3 ampere to get the same amount of flux density. Okay, but the maximum flux density Bmax is still the same. It's still the same, but you will reach the maximum flux density at higher value of current. Okay, so this is the advantage of air gap in designing inductor in your circuit. Okay, so this is what mentioned in the BH curve. So it based on the air gap length, based on the air gap length or the air gap volume. For larger air gap length, the characteristic is essentially much more linear. Okay, so you can see that if you increase the air gap, so as you can see, it is much more linear. You can get a more linear curve. More linear curve. The characteristic become non-linear as the air gap length decreases. So this one is, do you understand what does it mean by linear? Linear means something like straight line. It is much more straight line compared to this one. Okay, without the air gap, it is more curvy. It is more exponentially term. If you put in equation, if you find the equation for this one is much more exponential term. This one is much more linear within the operating point. Within the operating point. Okay. So this is what happens if you increase the air gap. Okay, it will be more linear. So based on the BH curve, okay, I can say that for a particular value of air gap length, the field energy is represented by the red area, okay, lambda axis and lambda I characteristic. The blue area between I axis and lambda I characteristic is known as the co-energy. So this area, the red area, the WF here, whereby when you integrate the I with the d lambda, so you get this area. Okay, you get this area. So this is known as energy or field energy. Okay, field energy, WF. But if you look at this area at the bottom here, which is the blue area, we denote this as WF prime. This is known as co-energy. Co-energy. Okay, co-energy, whereby you can find it by integrating the lambda with di. Okay, so basically this equation is something like, if you still remember the circuit theory, this is the step response. This is the step response. It's something like when you find the voltage is equal to the V final plus V initial minus V final E minus T over tau, if you still remember. So basically it is an exponential term. Exponential term, much more exponential term. Okay, but if you introduce an air gap, this line is much more linear. So I can say that it is much more linear. If it's non-linear, so we can say that the energy is, the area of the red area is smaller than the blue area. So it means that the energy is less than the co-energy. This is the energy. It's less than the co-energy. Energy stored in the magnetic system is less than co-energy. Co-energy is bigger. Okay, but if we operate in certain condition and we consider that this curve is almost linear, so we can say that if it is linear, so the energy is almost equal to the co-energy. Okay, so this is the equation that we normally use to define the energy and the co-energy. I said just now, the co-energy is defined as the integration of the curve, okay, whereby we define the curve as lambda. As I said just now, okay. Let's say this is the one that you have learned in circuit theory. So this is Vt. Vt is the lambda, and I is the time here, t. And you have to rearrange this equation such that you can get the t in terms of lambda. T in terms of voltage. The same goes to here. You have to represent this current. Okay, if you want to use current, so this current is in terms of lambda. But if you want to find lambda, you have to rearrange this equation such that you get lambda equal to the equation in terms of current. And you integrate with current, that is the co-energy. But if it is just a linear equation, so it's very simple. It's just like y equal to mx. If y is equal to lambda, m is equal to the slope, x is equal to I, so it is very simple to integrate. Okay. So from the figure of lambda I characteristic, okay, as we can see, the co-energy plus the energy is equal to lambda multiplied with I. So it is proof here that this is lambda and this is I. This is the length of the lambda and this is the length of the I. So if you add up the two area, so you get lambda multiplied with I. Simple as that. Okay. The co-energy, the blue area plus the energy, the red area, is equal to lambda I. And note that if the co-energy is greater than the energy, if the characteristic is non-linear, this is what I said just now, and if it is linear, so we can say that the energy and the co-energy is almost the same. Or if it is truly linear circuit, or if it is a straight line, is the true straight line, so the co-energy will equal to the energy. And I would like to stress here that the quantity of co-energy has no physical significance. The one that we concern is only the field energy. This is what we want to find because this is the energy stored in the magnetic system. But the quantity of co-energy has nothing to do with the physical magnetic system. However, it can be used to derive expression for force developed in electromagnetic system. Okay, we can use this co-energy to find the force and also the torque. Okay, for linear system it is force. for rotating system, it is the top developed in electromagnetic system. So I can say that in analysis, the core energy is also important. Okay, in analysis to find the force and torque, okay, the core energy is important. Okay, I think that's all for today. I want to stop here. We will continue next part tomorrow. Any question?
Thank you, Doctor.
No question?
No question at all.
Okay.
Doctor, the slide
Excuse me, Doctor.
we can get in e-learning, right? This slide.
I hope I can put it in the e-learning. Okay. Any other question?
Excuse me, Doctor.
Yes.
What did you just say right now for tomorrow? What?
We will continue with the topic tomorrow.
Oh, yeah, okay. Okay.
Because we have class tomorrow at 2. Right.
Yeah.
Okay. I think
So,
that's all.
Doctor, for the previous classes, other than this one, is it recorded or no?
No, only starting this one.